to go along with our work so far with synthetic division and polynomials, we're going to examine the rational zero theorem today. So a quick reminder before we start, the solutions, what we've called solutions, of a polynomial equation are the x-intercepts, where y equals 0. These are most frequently referred to as roots or zeros. And especially in today's notes, we're going to focus on the word zeros. And this is because they are the x values that give you 0 for y. For example, if you graph a quadratic equation, typically what we call the solutions are where the parabola intersects the x-axis. So those are also called roots or zeros. So what we're going to do is use synthetic division to confirm whether 5 is a 0 to this equation. And if you remember from our previous notes, we can use synthetic division to essentially substitute in a number for x to check the value of that function. And so if we do this with 5 and get 0 as the remainder, we know that 5 is a 0 of this function. So we'll set up our synthetic division problem here. And then we'll go through it. 1 times 5 is 5, minus 2 is 3, times 5 is 15, and we get 0. So because we get 0 here, yes, 5 is a 0 of this quadratic equation. Now, since this was a quadratic equation, I could have used factoring, I could have used the quadratic formula to also confirm this, but you can imagine for higher degree equations, this maybe is a simpler method, especially when you consider that the quadratic formula only works for quadratic equations. So now this brings us to the rational zero theorem, which states that any rational zero of a polynomial with integer coefficients, so just number coefficients, like 1, -1, 5, -5, must be a fraction p over q where the numerator is a factor of the constant term and the denominator is a factor of the leading coefficient. So what we are going to do is make a list of possible solutions using that fact, test them with synthetic division, and once we find a 0, then we can find the remaining zeros either in the same way, or if the resulting quotient is a quadratic polynomial, we can use factoring or the quadratic formula. Either way, repeat this until we find solutions equal to the degree of the polynomial equation. So if it's a degree 3 polynomial, we'll get 3 zeros. So all that to mean we can find a potential list of zeros and then from that, test them with synthetic division to see if we have a 0 there. So first, let's just practice finding that list of potential zeros. So here we have 4x squared minus 3x plus 2. We're going to find our p and q values. So p, these are the factors of the constant, which here is 2. Well, that's 1 and 2. Q are the factors of the leading coefficient, which here is 4, so 1, 2, and 4. And now our list of possible zeros are all the possible fractions p over q, positive and negative. And so for these numbers, those potential zeros are first 1 over 1, 2 over 1, and then 1 over 2, 2 over 2, which is just 1, which I already have, so I can skip that one. 1 over 4, that's 1/4, and 2 over 4, which is also 1/2, so I can skip that one as well. We don't need to write down duplicates. And so we have a list of 8, 4 positive and 4 negative numbers here that the zeros of my polynomial are in this list somewhere. So this is just a potential list of zeros. It's not all the zeros. We don't know which numbers it is yet. but we do know that our zeros are in this list. So for larger degree polynomials, this is quite helpful. So we have a place to start with synthetic division. All right, let's generate a few more here. We got our P numbers for example B, the factors of 9, that's 1, 3, and 9. And for Q, the factors of 5 are 1 and 5. So our potential zeros, P over Q, are positive and negative, 1 over 1, 3 over 1, 9 over 1, and then 1/5, 3/5, 9/5. So we have a list of 12 potential zeros here. 3 are 6 positives and 6 negatives. All right, moving on to C. Our P factors for 10 are 1, 2, 5, and 10. What's great about this problem is that our leading coefficient is 1, so that Q number is just 1, which makes our P over Q values a much smaller list. So that's just 1 over 1, 2 over 1, 5 over 1, and 10 over 1. So we have a list of 8 potential zeros here, of which 3, since it's degree 3, of which 3 of them are actually the zeros to our polynomial. So what do we do with this list? Well, after you generate the list, then we move on to step 2 here. Test them using synthetic division to try to find an actual zero. So let's do this. Now we're going to do the whole process. We'll use the rational zero theorem to find our P over Q values. Then we'll test them out to try to get an actual zero, and then find the rest by factoring. Technically, you could use the quadratic formula. All of our problems here will give us a quadratic, but factoring, I think, will be the simplest way to go here. So that's what I will do in these notes. And I'll mention this again when we get there. You could also use the quadratic formula. Okay, so first we have to do the same thing we just did and find all of our P's over Q's. So here, it's the factors of 18. That's 1, 2, 3, 6, 9, and 18. And our Q values, again, luckily is a 1. So that's just 1. So our list of P over Q numbers is just 1, 2, 3, 6, 9, and 18. I think I want to move that. I thought I wouldn't have space, but I think I do. Put that right there. All right, so now what we need to do with these numbers is test them one at a time to see if any of them are actual zeros. So we're going to set up a synthetic division problem here using the coefficients from the polynomial in the equation, which are 1, 8, 21, and 18. I'm going to try to leave plenty of space here because if a number doesn't work, I'm just going to erase the work and restart. So first let's try positive 1. Oh, and don't forget, these are positive and negative numbers for P over Q, plus and minus these numbers. So let's try positive 1. So 1 times 1 is 1, plus, right, add down, we get 9 times 1 is 9. Add down, we get 30 times 1 is, yeah, we're not going to get 0 here. Let's try negative 1. So 1 times negative 1 is negative 1. We get 7. Times negative 1 is negative 7, which is 14 times negative 1. That's not going to work either. So it's not 1 or negative 1. We can rule out the 1s. Let's go on to 2. We're just moving down our list. So 1 times 2 is 2. We get 10 times 2 is 20. This is 41. This isn't looking good. 82 is not going to get us 0 there. Let's try negative 2. 1 times negative 2 is negative 2. So that's 6. Negative 12. That's 9. Negative 18 and 0. So we know this is a 0. So -2 is one of our possible solutions. So from here, we could continue trying numbers, but there is a risk in that. So what I recommend instead, we're going to write out our new polynomial quotient, which is x squared plus 6x plus 9, just based off of those coefficients. And then let's go ahead and just factor this, because if this is equal to 0, if I factor it, then I can set each factor equal to 0 and solve that way. So we're looking for two numbers here that multiply to 9 and add to 6, which are 3 and 3. So if you are used to the big X organizer, that would be 9 here, 6 here, 3 and 3. So because we have a leading coefficient of 1, I can jump straight to my answers, x plus 3 and x plus 3. Those are my two binomial factors. And if I set those equal to 0, because they're the same, I'll get the same number. I get -3 for both of them. And so our 3 roots, even though we have one that repeats, I'm still going to include it in the list because it feels better to write a list of 3 here, are -3, -3, and -2. And this is also why I caution against just using synthetic division and going through the whole list, because if I did that here, I would only find 2 roots, -3 and -2, and I wouldn't know which one was a repeater, because we have to have 3 roots since the degree of the polynomial was 3. Okay, let's do that again. Our p-values here are the factors of 3, 1 and 3, and our q-values are the factors of 2, 1 and 2. So our p over q fractions are positive and negative, 1 over 1, 3 over 1, 1 over 2, and 3 over 2. Just squeeze that in there. And now we can use synthetic division with this polynomial. So 2, -5, -4, and 3. And we can begin. So let's try 1. 1 times 2 is 2. We get -3. That's -3. We get -7. That's not going to give us a 0. So let's try -1. -2, that's -7. 7 minus 4 is 3. Times -1 is -3. So we do get 0 here. That means -1 is one of our solutions. And again, I'm going to recommend we just write out this new quadratic polynomial, factor it, and solve. Now here I don't have a leading coefficient of 1, so I have to do a little more work. I need two numbers that multiply to 6 and add to -7. Those two numbers would be -6 and -1. So we split that middle term, right? 2x squared minus 6x minus 1x plus 3. And then we factor by grouping. So we can take out a 2x here, that leaves x minus 3. I can take out a -1, which leaves x minus 3. So there's one binomial factor, x minus 3. And my other one is 2x minus 1. Now I know I'm going to set these equal to 0. So I'm going to go ahead and do that here. Because I'm not actually looking for the factored form. I just want my factors so I can find my roots, right? So plus 3 on both sides here. I get x equals 3. Over here I'll add 1 and then divide by 2. So I get x equals 1/2. So my 3 roots here are -1, 1/2, and 3. So 1 root from my synthetic division and the other 2 from factoring what remains. Last one here, same process. My p-values are the factors of 8, 1, 2, 4, and 8. My q values are the factors of 3, 1, and 3. So let's generate our p over q possibilities here. Plus and minus 1 over 1, 2 over 1, 4 over 1, 8 over 1, 1 over 3, 2 over 3, 4 over 3, and 8 over 3. Taking up too much space, but that's okay. Hopefully one of our roots is in the whole number section. We won't have to get into the fractions. So let's do some synthetic division here. We're going to set up, we got 3, negative 13, 2, and 8. So bring that 3 down. Let's go ahead and try a 1. So 3 times 1 is 3, that's negative 10. Negative 10 plus 2 is negative 8. Times 1 is negative 8. We got that right away. That's always nice. So we got 1 is one of our roots. So now 3x squared minus 10x minus 8. We're going to factor by grouping. So negative 24 and negative 10. That would be a negative 12 and positive 2. So split that middle term into negative 12x plus 2x. Factor by grouping. We can take out a 3x here. That leaves x minus 4. And we can take out a 2 here. That leaves x minus 4. So my two factors are 3x plus 2 and x minus 4. Solving those little equations, I get x equals positive 4 here and negative 2/3 over here. So my three roots are 1, negative 2/3, and positive 4. Write that out in a list. There we go. So the rational zero theorem. It's a lot of work. It's a multi-step problem. Generate your list of P over Q, possible zeros. Test those zeros in synthetic division until you find a zero. And then factor what's left. Or again, you could use the quadratic formula. So factor or use the quadratic formula. But in most cases, I think factoring is the way to go. Just a little easier maybe, but up to you. And that will let you find the remaining two zeros here. Now, all of your practice problems are cubic equations like this. So this will be the same process you're going to take on your work.